My name is Philipp Grete, and I welcome you to this brief overview on our recent work on energy spectra and magnetohydrodynamic turbulence. This is well aligned with the overall theme of this meeting because it connects theory and simulations with a phenomenon that is observed in the universe on all kinds of scales, namely magnetized turbulence, which is of course also observed on galactic scales. As a brief background, I would first like to talk about hydrodynamic turbulence, where we in principle know the exact equations, but we don't know the solutions exactly. However, there exists a statistical description for some quantities in the stationary state, so when the overall system does not evolve from a statistical point anymore. Most famously, this corresponds to the kinetic energy power spectrum. On the bottom right, we have the energy on the y-axis and the scales on the x-axis, with the larger scales on the left-hand side and the smaller scales on the right-hand side. In the canonical picture, we have some kind of energy production mechanism or an energy mechanism that injects energy on the larger scales, resulting in turbulent or large-scale vertical motion, also called eddies, on the larger scales that break up into smaller and smaller and smaller scales until they're eventually dissipated on the very smallest scales. A key result in hydrodynamic, or specifically incompressible hydrodynamic theory, is that the energy transfer across scales in this intermediate range is constant. In addition, this also corresponds to the famous Kolmogorov slope of -5/3. So the energy spectrum has a power law of -5/3. In magnetohydrodynamics, the overall picture is a little bit more complex because in addition to the flow or fluid or plasma motion, we also have magnetic fields that's effectively frozen in. So for example, if you think about a spherical region in blue here that is threaded by magnetic field lines in black, if that spherical region starts to collapse, for example, under gravity, the magnetic field lines are dragged along, resulting in both bent field lines and a higher concentration. So eventually we will get a back reaction from the magnetic fields on the flow because we have a higher magnetic pressure or energy in the central region, as well as a magnetic tension force that acts to straighten the field lines again. So it acts against the curvature. So there is a rich interaction between kinetic and magnetic energy budgets, and we would like to know more about how this actually works. How can we study these different energy transfers in energy dynamics? For this, several years ago, we extended an existing framework from the incompressible to the compressible regime, where we can analyze the detailed dynamics of how, for example, the kinetic energy spectrum or the magnetic energy budget interacts with itself. So for example, we do have the kinetic energy cascade, so energy going from one scale to the next smaller scale to the next smaller scale, or a magnetic energy cascade, but also looking at how energy is transferred between the budgets, for example, through magnetic tension. In practice, what we are doing is we run a simulation of driven MHD turbulence, where on the right-hand side, you see the scales, all scales in the top left panel. And when we apply the energy transfer analysis, we separate these scales into large scales, into intermediate scales, into smaller scales, so that you can see we have eddies of all kinds of sizes and calculate how those interact through different mediators like magnetic tension or magnetic cascade, and how strong the individual transfers are. But what motivated that kind of study? Well, there is a lot of theories for how the energy spectrum should look like in the stationary regime for MHD turbulence. Most of the time, they are concerned with the total, so magnetic plus kinetic energy spectrum. However, when you start to look at the spectra separately, so kinetic and magnetic energy spectrum, an interesting dynamics emerge. Specifically, the spectra did not scale with -5/3 as you would expect from hydrodynamic theory. In the plot here, you see the spectra, the kinetic energy spectra as the solid lines and the magnetic energy as dashed dotted lines, compensated by 4/3 by various groups reported in literature. And as you can see, we now, given that these are compensated, have almost straight lines on the intermediate scales for all these different works that use various numerical methods, from spectral method to finite difference to finite volume methods. If we now look at the dynamics in the simulation that we ran in more detail, you will see how the temporal evolution of the mean kinetic in green, in blue, magnetic in orange, and the ratio in green on the left-hand side, and the instantaneous energy spectra on the right-hand side. So initially, we have very steep spectra because we only have energy on the very largest scales. But once the system starts to evolve, you can see on the right-hand side that the magnetic energy becomes first dominant on the very smallest scales, and that over time, the crossover where magnetic energy becomes dominant on the smaller and smaller scales grows towards the left. Also note the inset, where we plot the same range as in the larger panel, only that the energy spectra here are again compensated by -4/3. And as you can see, in addition to the crossover moving towards the left during later times, also we see that the kinetic energy spectrum becomes shallower and shallower and eventually reaches a slope that is roughly corresponding to -4/3. And in the end, once we reach a state of stationary turbulence, the statistics don't change anymore, and the spectra are approximately constant between individual snapshots in that simulation. Now, I mentioned the energy transfer analysis. We applied the energy transfer analysis to this simulation, and we are specifically now looking at the energy balance at intermediate scales. So the scales where we are in the power law regime. On the bottom, you see, or on the x-axis, you see the evolution over time again, and we now look at the net rate of change in the kinetic energy at the top panel, and at the bottom in the magnetic energy. So a positive number corresponds to a net growth of energy, a negative number corresponds to a net loss of energy on intermediate scales. And overall, towards the late times, we need to overall sum up to 0 because we are in the stationary regime, so there can't be any net loss or net growth of energy because the spectra are statistically constant. And this is exactly what we observe. So the sum is basically 0 in both cases over time, but all the other individual transfers are non-zero. Specifically, when we are looking at the energy transported through the cascades, so the blue lines, the top, the kinetic cascade, and the bottom, the magnetic cascade, they're both negative. So they would result in the net loss of energy in that kind of simulation. However, the orange lines, which corresponds to energy transfers through magnetic tension, are positive in both cases. And they're actually resulting in overall energy balance. So in other words, the kinetic and magnetic energy cascades are not balanced and would result in a net loss, which is counteracted by transfers between the budgets by magnetic tension. Next, we're going to look at the cross-scale fluxes. So how much energy is going from the larger scales across some scales towards the smaller scales. Again, we look at the cross-scale flux in the on some intermediate scale over time. As a reminder, in hydrodynamic turbulence, the cross-scale flux from the kinetic cascade is the only means of energy being transferred to smaller and smaller scales. So in the hydrodynamic case, we would expect it to grow while the turbulence is still driven, and then eventually become constant over time in the stationary regime, indicated here by the dashed blue line. However, in the case with magnetic fields present, we see again that the kinetic energy cascade initially grows, but then declines again and is eventually zero. However, the cross-scale flux through magnetic tension is becoming stronger and stronger and stronger, and eventually is completely dominating the overall cross-scale flux from the larger scales to the smaller scales in magnetized turbulence. With that, I would like to conclude emphasizing that the dynamics in MHD are fundamentally different than hydrodynamic turbulence, and that magnetic tension dominates the cross-scale fluxes, but also results in a balancing the net energy changes at all scales. So we interpret this as that the kinetic energy spectra or the kinetic energy cascade is effectively depleted by cross-scale, by the magnetic tension, which results in less efficient energy transfer, and that again results in a shallower slope in the kinetic energy spectrum. For more details, I encourage you to look at our paper that has been published in FJ this year, or also feel free to talk to me during the meeting. Finally, I hope that this work will inspire refined theories of MHD turbulence that also can explain on why we observe a slope that is more closer to -4/3 than to 5/3. Thank you for listening, and see you on Friday.